There is something moving through you right now that has no source you can point to. Not a feeling, not electricity, something older than both. Physicists call it a field, something that fills every cubic centimeter of space, including the space inside your body, the gap between your thoughts, the silence between your heartbeats. And here's the part no one quite prepares you for. This field is not empty. It is not passive. It is doing something constantly, even in the darkest, most sterile vacuum in the universe. It is pushing. And the strange implication of that push, what it means for the shape of reality, for the end of everything, for whether anything you can see tonight will still be visible in 100 billion years, is what this video is about. Make yourself comfortable. Let the room go quiet around you. Stay with me through this one. The field that is eating the universe. Chapter 1: The ground beneath nothing. Start with something you probably believe without realizing you believe it. Empty space is empty. It sounds almost too obvious to say out loud. Of course, empty space is empty. That is what empty means. You remove the stars, the gas, the dust, the radiation, the light, the matter. You remove everything, and what remains is nothing. A pure nothing, a vacuum. And a vacuum, by definition, is the absence of substance, the absence of pressure, the absence of anything that could push or pull or interact or change. That is the intuition. It is so natural that it barely feels like an assumption. It feels like a definition. And it has been with us for a very long time, embedded so deeply in the way we think about space that questioning it can feel almost grammatically awkward. But it is wrong. Not approximately wrong, not wrong in some marginal technical sense, not wrong in a way that only matters at extreme conditions nobody will ever encounter. It is wrong in a way that bears directly on why the universe is the size it is, why it is accelerating, why the night sky will be empty in 1 trillion years, and why some of the most careful and brilliant physicists working today describe one particular consequence of this wrongness as the most embarrassing number in the history of science. The ancient Greeks argued about this. Some of them, Democritus, Leucippus, believed that the void was real, that atoms moved through it the way fish move through water, that emptiness was not just possible but necessary for anything to move at all. If everything were full, nothing could go anywhere. The void was the freedom that motion required. Aristotle disagreed strongly. He believed that nature abhors a vacuum, that the universe would always fill in any emptiness that tried to form, that the void was not a thing in the world but a philosophical fiction, an idea you could discuss but could not point to. For Aristotle, space was not a container waiting to be filled. Space was defined by the things in it. Remove the things and the space itself disappears. There is no empty box. There is only the box with things in it, and the question of what is inside becomes the question of what those things are. For roughly 2,000 years, Aristotle won this argument, not because his reasoning was formally proved, but because it matched intuition, because no one had a way to test it, because the technology to make an actual empty region of space did not exist. Then came the 17th century, and a German scientist and engineer named Otto von Guericke built a machine that could pump the air out of a sealed container. He built a piston pump, careful and precise, and connected it to a sealed sphere and pumped until the air inside was as thin as he could make it. The result was not perfect. Atoms are hard to catch and harder to stop, but it was close. It was closer to empty than anything a human being had ever deliberately created. And then he did something theatrical, as good scientists sometimes do. He placed 2 hollow bronze hemispheres together, sealed them, evacuated the air from the space between them, and summoned horses. 2 teams of 8, one on each side, 16 horses in total, and had them pull. They strained, they kicked up dust, they pulled with everything their bodies could offer. The hemispheres held. Not because of some mysterious force locking them together, but because of the air pressure on the outside, the pressure of all the air in the atmosphere pressing inward on the evacuated sphere. Without anything inside pushing back, the external pressure was overwhelming. The horses could not overcome it. This was the Magdeburg Hemisphere's experiment, and it was the first direct demonstration that a vacuum, not a philosophical vacuum, but a physical one, a region with substantially less matter than its surroundings, could be created and could have measurable consequences. The void was real. The void did something. The obvious next question was, what is actually in there? The 17th and 18th and 19th centuries offered an answer that turned out to be wrong, but was wrong in an interesting way. The answer was the luminiferous ether. Light behaves like a wave. Waves, as far as anyone in that era knew, require a medium to propagate through. Sound waves travel through air. Water waves travel through water. Light travels through what? Through the ether. A perfectly transparent, perfectly elastic, perfectly pervasive medium that filled all of space, including the evacuated space inside von Guericke's sphere. The vacuum was not truly empty, it was full of ether. This was a reasonable hypothesis. It had the form of an explanation. And in 1887, it was tested by Albert Michelson and Edward Morley in a basement in Cleveland, Ohio, using an instrument called an interferometer that could measure extraordinarily small differences in the speed of light. If the ether existed, the Earth moving through it should produce a slight headwind for light traveling in one direction and a slight tailwind for light traveling in the other, similar to how a swimmer moving through water encounters more resistance going one direction than the other when the current is flowing. The interferometer was designed to detect this difference. It found nothing. The speed of light was the same in all directions to the precision of the measurement. No headwind, no tailwind, no ether. The most sensitive measurement of its kind ever made had produced a null result, and a null result in this case was the most revolutionary thing that could have happened. Space was empty after all. Except that it was not. The 20th century arrived and quantum mechanics arrived with it, and everything became strange again. Quantum mechanics, the set of principles that describe the behavior of matter and energy at very small scales, came with a peculiar and at first deeply uncomfortable implication. It said that the vacuum, the lowest energy state of any physical system, could not be a perfect nothing. It could not be zero. It could not be still. This is not philosophy. This is mathematics. And the mathematics is grounded in a principle discovered by Werner Heisenberg in 1927, the uncertainty principle. You have probably heard this described as the idea that you cannot measure the position and momentum of a particle simultaneously with perfect precision. That is correct, but it understates the depth of the principle. The uncertainty is not about measurement. It is about what it means for a particle to have a definite position and momentum at the same time. The uncertainty principle says that having both simultaneously precisely defined is not something that particles do. It is not a matter of disturbing the system with your measurement. It is a feature of what the system is. And this principle applies not just to particles but to fields. A quantum field, the fundamental objects of quantum field theory, the framework that underlies all of particle physics, obeys the same rule. A field cannot have both a precisely defined value and a precisely defined rate of change. If you try to pin a field to zero, perfectly still, perfectly flat, perfectly absent, you have specified both its value zero and its rate of change also zero, which is exactly what the uncertainty principle forbids. The field must fluctuate, it has no choice. The fluctuations are not caused by anything. They are not the result of thermal energy or radiation or external perturbation. They are the consequence of what it means to be a quantum field. They are intrinsic, they are irreducible. They cannot be removed or suppressed or extracted. And those fluctuations carry energy. That energy is called the zero-point energy of the vacuum. It is the energy that remains when you have removed everything else, all the particles, all the radiation, all the thermal energy, all the kinetic energy, and you are left with just the quantum fields in their lowest possible state. And that state still has energy. A substantial, real, physically consequential energy that permeates every point in space. Take a breath. The air you just inhaled is full of nitrogen molecules, oxygen molecules, a little carbon dioxide. And between each of those molecules, in the spaces too small to see but too numerous to count, there is vacuum. And in that vacuum, the zero-point energy of the quantum fields exists, as it exists everywhere always, because it cannot not exist. This is the ground beneath nothing, and it is not nothing. Chapter 2: What a field actually is. Let us pause here and do something that will pay dividends for the rest of this video. Let us actually understand what a field is. Most people have a rough intuition about fields from school: a magnetic field, an electric field, a gravitational field. These are the invisible structures that surround magnets and charged particles and massive objects, and that reach out through space to push and pull other things. That intuition is approximately right, but it does not go deep enough to understand what quantum field theory is actually claiming about the nature of reality. In physics, a field is a quantity that has a value at every point in space, not a property of an object, not a force radiating outward from a source and thinning with distance. A thing in itself, defined everywhere, at every moment. Temperature is a useful everyday example. At every point in this room, every cubic centimeter of air, every slice of wall, every point on the floor and ceiling, there is a temperature. You do not have to actively assign the temperature to those locations. It is already there. The temperature field is defined over the entire room. You can measure it at different places and find different values, but the field itself is the complete description, the entire map of temperatures over the entire space. Now make that richer. Instead of a single number, one temperature at each point, imagine a quantity that has both a magnitude and a direction at each point. Wind is the atmospheric example. At every point in the atmosphere, the air has both a speed and a direction of motion. Together, those two pieces of information, magnitude and direction, constitute the wind vector at that point. The wind field is a vector field, more information per point, more structure. Now abstract further. Imagine a field that is not just a number or a vector, but a mathematical object with internal structure, with symmetries, with the ability to transform under rotations or reflections in ways that reveal deep features of reality. These are the fields of quantum field theory, and they are both more abstract and more fundamental than either of the examples above. The key claim of quantum field theory, the framework that underlies the standard model of particle physics, our most comprehensive and successful theory of fundamental interactions, is that the basic constituents of reality are not particles. They are fields. Particles in this framework are not tiny balls of stuff. They are vibrations in the field. An electron is a localized excitation of the electron field. A photon, a quantum of light, is a localized excitation of the electromagnetic field. A quark is an excitation of a quark field. The Higgs boson, discovered at the Large Hadron Collider in 2012, is an excitation of the Higgs field. Each of these fields extends through all of space. The electron field is everywhere inside stars, in the void between galaxies, in the space between your cells. The electromagnetic field is everywhere. The quark fields are everywhere. There are about 17 fundamental fields in the standard model, each with its own identity, its own rules of interaction, its own set of excitations. They overlap, they interact with each other. They combine in extraordinary complexity to produce everything we see. And each one of them has a ground state, a state of minimum energy, a state where there are no excitations, no particles, no vibrations, no activity that we could detect as matter or radiation. That ground state is the vacuum. And in the ground state, as we have just seen, the field cannot be zero. The field cannot be still. Heisenberg's uncertainty principle prevents it. So the ground state of every field in the Standard Model is a state of ceaseless quantum fluctuation. Not random fluctuation, not meaningless fluctuation, but precisely the minimum fluctuation required by the mathematics of quantum mechanics. These fluctuations are sometimes described as virtual particles. The language is evocative but slightly misleading. Virtual particles are not particles that briefly exist and then disappear. They are a way of calculating the effects of quantum field fluctuations using a particular mathematical shortcut called Feynman diagrams. The fluctuations themselves are real. The language of particles popping in and out of existence is a useful metaphor but should not be taken too literally. What is real is the energy. What is real is the fluctuation. What is real is that the vacuum is not empty. There is a beautiful and somewhat unnerving experimental confirmation of this. In 1948, the Dutch physicist Hendrik Casimir predicted that if you placed two perfectly conducting, perfectly flat metal plates very close together in a vacuum, with nothing between them, the plates would experience an attractive force pulling them toward each other. Not gravity, not electromagnetism in the conventional sense. A force arising purely from the quantum vacuum between them. Here is the idea. The vacuum contains quantum fluctuations of the electromagnetic field. These fluctuations exist at all wavelengths. Between the plates, only certain wavelengths are allowed, the ones that fit between the plates. Outside the plates, all wavelengths are allowed. So the fluctuations outside the plates are more numerous than the fluctuations inside. The pressure from outside exceeds the pressure from inside, and the plates are pushed together. This is the Casimir effect. And it has been measured many times by multiple groups. The force is there. It is small. We are talking about forces relevant only on scales of nanometers, but it is real, and its measured value matches the theoretical prediction. The vacuum is doing something. The vacuum exerts forces. The vacuum is not empty. This is not an exotic claim about the edge cases of physics. This is confirmed by tabletop experiments. The Casimir effect is so well established that it is an engineering consideration in the design of nanoscale machines. Devices called MEMS, microelectromechanical systems, sometimes have components so small and so close together that the Casimir effect can cause them to stick. Engineers have to design around it. The ground beneath nothing is not nothing. Chapter 3, the most embarrassing number in science. Let us now talk about the calculation. Physicists, given that the vacuum has energy, naturally want to calculate how much. This is the kind of thing physicists do. You have a theory, the theory makes a prediction. You do the calculation, you compare to measurement, and then you either celebrate or revise. In this case, neither option is entirely available, because the calculation returns a number that does not match the measurement by the largest factor in the history of science, and we do not know how to revise the theory to fix it. The calculation in outline works like this. The zero-point energy of the vacuum comes from the ground state energies of all the quantum fields, summed over all possible modes, all the different wavelengths and frequencies at which those fields can fluctuate. In principle, this sum should include all frequencies up to infinity. When you do that, you get an infinite answer. Infinity is clearly wrong, so physicists apply what is called a cutoff. They argue that our theory, quantum field theory as formulated in the Standard Model, is almost certainly not valid up to infinite energies. It is an effective theory, valid in a particular regime. Above some energy scale, a better theory, presumably one that incorporates quantum gravity, takes over. The Standard Model breaks down, so we should only trust its predictions up to the scale where it breaks down. The natural candidate for that cutoff is the Planck scale. This is the energy at which quantum gravitational effects are expected to become important, where the quantum fluctuations of spacetime itself are comparable in size to the features we are calculating. The Planck scale is approximately 10 to the power of 19 GeV, where a GeV is roughly the rest energy of a proton. When you calculate the vacuum energy density using the fields of the Standard Model, summed up to the Planck cutoff, you get a number. It is a very large number, roughly 10 to the power of 113 joules per cubic meter. This is the theoretical prediction for how much energy should be in every cubic meter of empty space. Now you go to the observatories, you measure how the universe is expanding. You fit the data to the equations of general relativity. You find that the expansion is accelerating, and you determine the value of the cosmological constant, the energy density of the vacuum, that best fits the data. The measured value is approximately 10 to the power of -9 joules per cubic meter. Compare those two numbers. The prediction is 10 to the power of 113. The measurement is 10 to the power of -9. The difference is a factor of 10 to the power of 122. That is 1 followed by 122 zeros. To give you some sense of what that means, the ratio of the size of the observable universe to the size of a proton is roughly 10 to the power of 42. That sounds enormous. It is enormous, but it is not even close to 10 to the 122. The number we are dealing with is so much larger than the ratio of the universe to a proton that comparing them feels absurd. This discrepancy has a name. It is called the vacuum catastrophe, or the cosmological constant problem, or in certain physicist moods, just the disaster. It is widely considered the worst prediction in the sense of the largest discrepancy between theory and experiment in the history of science. And what makes it so unsettling is not just the size of the discrepancy, but what it implies. If the vacuum energy density were actually as large as the Standard Model calculation suggests, the universe would have expanded so rapidly, so violently, so immediately after the Big Bang that matter could never have clumped together. The gravitational force between particles would have been completely overwhelmed by the expansion of space. Atoms could not have formed, molecules could not have formed, stars could not have formed, galaxies could not have formed, you could not have formed. The universe would have been an expanding, cooling gas of particles spreading ever thinner into a void, with nothing ever grouping into anything complex ever. But it did not do that. You are here. The universe is here, full of structure, galaxies, stars, planets, chemistry, biology, consciousness asking about itself, which means the vacuum energy is not 10 to the 113. It is 10 to the -9. It is 122 orders of magnitude smaller than the theory predicts. Why? We do not know. This is the honest answer. We do not know. We have several candidate explanations, and none of them is satisfying. One is supersymmetry. This is a theoretical symmetry that, if exact, pairs every bosonic particle with a fermionic superpartner. Bosons and fermions contribute to the vacuum energy with opposite signs. One type of particle's contribution is positive, the other's is negative. If supersymmetry were exact, the contributions would cancel perfectly. The vacuum energy would be zero. But supersymmetry is not exact. We know this because we do not observe superpartners with the same masses as their Standard Model counterparts. If we did, we would have detected them long ago. Supersymmetry, if it exists at all, must be broken, meaning the superpartners are heavier. And when you include broken supersymmetry in the calculation, the cancellation is imperfect. You still get a large number, just slightly smaller, not nearly small enough. The Higgs boson discovery at the LHC in 2012 put further constraints on supersymmetric theories. The Higgs mass of approximately 125 GeV is in a range that is consistent with some versions of supersymmetry, but rules out many others. And despite years of searching, no superpartner has been directly detected. Another candidate is anthropic reasoning, as it is sometimes called. Perhaps the vacuum energy is small because it has to be, not because some mechanism sets it to a small value, but because in a universe where it is large, nobody exists to measure it. If our universe is one of many, if there is a vast landscape of possible universes, each with different fundamental constants, each explored by quantum processes during some primordial period, then the overwhelming majority of those universes have large vacuum energies and no structure. Only the rare ones with small vacuum energy develop galaxies, stars, planets, and observers. We find ourselves in such a universe because those are the only ones with anyone in them. This explanation troubles many physicists deeply, not because it is obviously wrong, but because it feels like giving up. If the answer to why is the cosmological constant small is because if it were large, you would not be here to ask, then in some sense the explanation explains nothing mechanically. It does not tell you which process sets the value. It does not connect to any deeper physics. It is a selection argument, a statement about which universes can be observed, not about which processes create them. Whether this constitutes a genuine scientific explanation or a sophisticated evasion is a matter of active debate among physicists and philosophers of physics. A third possibility is simply that we are missing something, that there is a principle, a symmetry, a structure in nature that we have not yet discovered, and that principle naturally constrains the vacuum energy to the small value we observe. This explanation is unsatisfying in a different way. It is unfalsifiable as stated because it explains nothing until you actually find the missing principle. But it has the virtue of being almost certainly true in the sense that our current theories are almost certainly incomplete. We are missing something, we just do not know what it is. And in the gap between what we calculate and what we observe, in the 122 orders of magnitude between theory and measurement, something real is hidden. Chapter 4: The Discovery That Changed Cosmology. On the night of January 28, 1998, a preprint appeared on an astrophysics archive that would eventually reshape how we understand the universe. Actually, it was not one night. It was a press conference and a paper, and the culmination of years of painstaking work by two competing teams who had each been spending their nights pointing telescopes at dead stars in distant galaxies. Let me give you the setup. By the mid-1990s, cosmologists were fairly confident that the universe had begun in a hot, dense state, the Big Bang, and had been expanding ever since. The expansion was well established. Hubble had seen it, and subsequent measurements had confirmed it countless times with increasing precision. The open question was whether the expansion was slowing down. It should have been slowing down. Everything in the universe, every galaxy, every star, every atom has mass, and mass attracts. The mutual gravitational attraction of all this mass spread through the expanding universe should act as a brake. The expansion should be decelerating, not stopping probably, but at least slowing. The question was how much. The way you measure the deceleration or the acceleration, though no one expected acceleration, is to measure how the expansion rate has changed over time. To do that, you need to look at very distant objects. Looking at distance is looking back in time, because the light from those objects has been traveling toward you, and the universe has been expanding while it traveled. The light was emitted when the universe was younger, smaller, expanding at a different rate. By comparing the actual distances to those objects with the distances you would expect from a universe expanding at a constant rate, you can determine whether the rate has increased or decreased. You need very bright, very consistent objects to measure distances reliably over billions of light years, and the best tool available was a particular type of stellar explosion, the type Ia supernova. A type Ia supernova happens when a white dwarf, the collapsed remnant of a star not quite massive enough to become a neutron star or black hole, slowly accumulates material from a companion star. As the material piles up, the white dwarf's mass increases. At a precise mass, roughly 1.4 times the mass of the Sun, known as the Chandrasekhar limit, the white dwarf can no longer support itself. It collapses and then explodes in a thermonuclear detonation so powerful that, for a few weeks, it outshines the entire galaxy containing it. Because the explosion always occurs at the same mass threshold, it always releases roughly the same amount of energy. With careful calibration, accounting for how the light curve evolves over time, type Ia supernovae can be standardized to be reliable distance indicators. You know how bright they actually are. You measure how bright they appear. From the difference, you calculate the distance. Two groups set out to do this systematically at large distances, using newly powerful digital cameras on ground-based and eventually space-based telescopes. The Supernova Cosmology project, led by Saul Perlmutter, and the HISE Supernova Search Team, led by Brian Schmidt and including Adam Rees as a key analyst. The teams were rivals, the rivalry was productive and occasionally tense, and in early 1998, both teams independently found the same thing. The distant supernovae were fainter than expected. Not dramatically fainter, not bizarrely fainter, just slightly, but in a systematic way, consistent across the sample, consistent with both data sets. Fainter means farther away than expected. Farther away than expected, given the expected deceleration, means the universe has not been decelerating. The distance we would expect from a decelerating universe is slightly less than the distance we would expect from a non-decelerating universe, which is slightly less than the distance we observe. The expansion has been speeding up. The universe is accelerating. When Rees first saw the numbers, he reportedly checked for errors for weeks. The result was so unexpected, so contrary to the physical intuition of the day, that the first assumption had to be that something had gone wrong. Maybe the distant supernovae were being dimmed by dust between the galaxies. Maybe the supernovae in the early universe were intrinsically different from nearby ones, less bright for some evolutionary reason. Maybe the calibration was off. They checked, both teams checked, separately and thoroughly. The systematic errors they could identify were not large enough to explain the discrepancy. The result survived. In 1998, both papers were published. The universe was accelerating. Something was causing the expansion to speed up. Something with the properties of a repulsive energy built into the fabric of space itself. Einstein had introduced a cosmological constant, a term in his field equations that could play exactly this role back in 1917 in order to produce a static universe. When Hubble discovered the expansion in 1929, Einstein dropped the constant and called it his greatest blunder. Now it was back, not to produce a static universe, but to produce an accelerating one. The observations demanded it. The cosmological constant was not a mistake, it was real, it was there. Its value was small, far smaller than any theoretical prediction, but it was definitively non-zero, and it was driving the universe to expand at an ever-increasing rate. Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics in 2011 for this discovery. And the discovery forced a reckoning with something we already had in our equations but had never taken seriously: the energy of the vacuum, dark energy, the field that permeates everything and pushes space apart. Chapter 5: What is actually happening to space? I want to make sure we are all working from the same picture of what the expansion actually is, because it is not what it intuitively seems. The universe is not a sphere of matter exploding into an empty surrounding void. There is no center point from which everything is flying outward. There is no edge of the universe moving through a larger, pre-existing space. What is expanding is space itself, the metric, the mathematical structure that defines distances between points is growing. Every point in space is getting farther from every other point in space, not because anything is moving through space, but because the space between things is increasing. Picture a coordinate grid drawn on a rubber sheet. As you stretch the sheet uniformly in all directions, every point on the grid gets farther from every other point. No point is special, there is no center of the stretching. From the perspective of any point on the grid, all the other points appear to be moving away. And crucially, more distant points appear to be moving away faster, not because they are moving faster through the grid, but because there is more grid between them and you, all of it stretching simultaneously. This is the Hubble expansion, the measured relationship between distance and recession speed. The Hubble constant tells you the current rate at which the grid is stretching per unit of distance. More distance, more grid, more stretching, higher apparent recession speed. Now add dark energy. In a universe with only matter and radiation, the expansion decelerates. Gravity, the mutual attraction of all the matter, pulls everything together, and while that pull is not strong enough to reverse the expansion, it slows it down. The grid stretches, but the rate at which it stretches decreases over time. In our universe with dark energy, something is actively countering that deceleration. The cosmological constant, the energy of the vacuum, acts like a pressure built into space itself. As space expands, the vacuum energy density does not change because it is a property of space rather than a property of the stuff in it. Every new cubic meter of space that comes into existence has the same vacuum energy as every old cubic meter. So unlike matter, which dilutes as the universe expands, dark energy maintains a constant density. And a constant uniform energy density in space produces a repulsive effect in Einstein's equations. Not because it acts like a conventional force, it does not push particles apart the way charged particles repel each other. Rather, the negative pressure associated with the vacuum energy changes the geometry of spacetime in a way that causes the expansion rate to increase over time. At early times when the universe was younger, smaller, denser, matter dominated. The energy density of matter was large enough that it outweighed the cosmological constant and the expansion decelerated, but matter dilutes as the universe expands. As the universe grew larger, the matter density fell. The dark energy density stayed constant. At some point, approximately 5 to 6 billion years ago, they became equal. And after that, dark energy won. The expansion began to accelerate. We live in the era of accelerated expansion. It began a few billion years ago, and it will continue indefinitely, increasingly dominating the dynamics of the universe. The consequence of this acceleration is a cosmic horizon. Light travels at a finite speed. The universe is expanding at a rate that, at sufficient distances, becomes large enough that the space between us and a distant galaxy is increasing faster than light can cross it. This does not mean light is moving backward. It means the destination is receding faster than the messenger can travel. Think of it like trying to walk from one end of a conveyor belt to the other, where the belt is moving away from you faster than you can walk. You will never reach the other end, not because you are too slow, but because the belt between you and the end keeps growing. Galaxies beyond a certain distance, the cosmic event horizon, are already in this situation. Their light is moving toward us, but the space it has to cross is expanding faster than the light can traverse it. That light will never reach us. As dark energy continues to drive the expansion to accelerate, this horizon shrinks. More and more galaxies cross from inside the horizon to outside it. Once a galaxy crosses, its light is no longer approaching us. It is, in a meaningful sense, no longer part of our observable universe. It fades. Its light stretches to ever longer wavelengths, redshifting past radio waves, past anything detectable, until it becomes, for all practical purposes, gone. There are currently on the order of 2 trillion galaxies in the observable universe. Most of them are already receding very rapidly. In about 100 to 150 billion years, the galaxies outside our local group, the gravitationally bound cluster of galaxies that includes the Milky Way and Andromeda and their satellite galaxies, will have receded beyond the horizon. The sky will appear to contain only the local group, which by that time will have merged into a single large elliptical galaxy. From the perspective of a civilization living in that future galaxy, the universe will look nearly empty. They will see stars, they will see their own galaxy, they will see darkness in every other direction, a darkness that looks pristine and absolute. They will have no way to know that, behind that horizon, there are 2 trillion galaxies they cannot see, each teeming with its own stars and planets, and perhaps its own kinds of complexity. They will look at the sky and see nothing and conclude, reasonably but incorrectly, that there is nothing there. Unless they find old records, unless the physics and cosmology of their era preserves the knowledge of earlier observations, in which case they will have to take on faith what their instruments can no longer confirm, that the universe was once full and is now hidden, and that the darkness around them is not the truth of the universe but merely the reach of their light. This is, in a quiet way, one of the more unsettling implications of dark energy. Not what it does to matter, not the big rip or the heat death, but the silence it brings. Chapter 6, The Far Future in Numbers. The far future of the universe is something physicists can calculate with reasonable confidence within the constraints of our current theories. What they find is a sequence of eras, each almost unimaginably longer than the last, separated by transitions that are either dramatic events or barely noticeable depending on your timescale. We are currently in what cosmologists call the stelliferous era, the age of stars. This era began a few 100 million years after the Big Bang, when the first stars ignited. It will last until roughly 100 trillion years from now, 10 to the power of 14 years, when the last stars burn out. That is an incomprehensible span of time by human standards. The current age of the universe, 13.8 billion years, is on the order of 10 to the 10 years. The end of the stelliferous era is at 10 to the 14. We are not even 1% of the way through it. During the stelliferous era, stars of all types live and die. The most massive stars, the blue giants that burn brilliant and hot, exhaust their fuel in a few million years, explode as supernovae, and leave neutron stars or black holes behind. The smallest stars, the red dwarfs, faint and cool and miserly with their hydrogen, burn for hundreds of billions of years. The last red dwarfs will still be glowing when the universe is 100 times its current age. As the stelliferous era ends, the raw material for new star formation, the molecular hydrogen clouds, the collapsing nebulae, will be exhausted. Stars will stop forming, the last ones will burn out, the galaxy will darken. Stellar remnants, white dwarfs, neutron stars, the occasional black hole will carry on, but they will be inert, slowly cooling. The galaxy will become a graveyard of dead stars orbiting each other in the dark. This transition to what is called the degenerate era happens so slowly that from any given moment inside it, nothing seems to be happening. The universe is dark but stable, cold but not yet dead. The degenerate era lasts from roughly 10 to the 14 years to roughly 10 to the 36 years. During this time, the white dwarfs cool, neutron stars cool. The cosmic background radiation, the afterglow of the Big Bang, which currently has a temperature of about 2.7 Kelvin, continues to redshift and cool as the universe expands, dropping toward absolute zero. Randomly, occasionally, over vast timescales, events occur. A brown dwarf, a failed star that never ignited, might collide with another brown dwarf and produce enough heat to briefly reignite fusion. A white dwarf might accrete material from a companion and produce a very late type Ia supernova. Gravitational interactions will slowly eject most stars from galaxies over timescales of 10 to the 19 years, far longer than the stelliferous era, leaving only black holes at the galactic centers and a sparse scatter of remnants in the intergalactic medium. After roughly 10 to the 36 years, proton decay may begin to matter if protons decay. This is uncertain. Grand unified theories predict that protons are not perfectly stable, that they will eventually decay into lighter particles with a half-life somewhere around 10 to the 31 to 10 to the 36 years. We have searched for proton decay with enormous underground detectors and have not yet seen it, which puts lower bounds on the proton lifetime but does not tell us whether it happens at all. If protons decay, the white dwarfs and neutron stars of the degenerate era will slowly dissolve. Their constituent protons will decay into lighter particles, positrons and pions, ultimately, which themselves annihilate or decay. The white dwarfs and neutron stars will fade over timescales of 10 to the 37 to 10 to the 40 years, leaving nothing but a diffuse, cooling gas of elementary particles. If protons do not decay, the white dwarfs and neutron stars persist longer. Over extraordinary timescales, 10 to the 65 years for stellar mass objects, quantum tunneling can cause them to eventually collapse into black holes. Quantum tunneling is the mechanism by which particles occasionally cross barriers they classically cannot. It is the basis of nuclear fusion in stars and radioactive decay in unstable isotopes. Given enough time, it is also the mechanism by which any large object can randomly rearrange itself into a more compact configuration. The probability is vanishingly small per unit time, but over timescales of 10 to the 65 years, it becomes relevant. What remains at the end of the degenerate era, whether protons decay or not, is a universe of black holes. All the original matter has either decayed or collapsed. Black holes are all that remains. Then comes the black hole era, which runs from roughly 10 to the 40 years to roughly 10 to the 100 years. Black holes are not immortal. Hawking radiation, the slow emission of thermal radiation from the event horizon, arising from quantum effects near the horizon, causes them to lose energy and mass over time. The process is extraordinarily slow. A stellar mass black hole evaporates on timescales of roughly 10 to the 67 years. A supermassive black hole, the billion solar mass variety that sits at the center of large galaxies, takes roughly 10 to the 100 years to evaporate. But evaporate they do. What is emitted during evaporation is thermal radiation, photons, gravitons, and eventually, as the black hole gets smaller and hotter, a variety of more massive particles. In the final moments of evaporation, a black hole releases an enormous burst of energy as it reaches its final mass and temperature spike. Then it is gone. After the black hole era, the universe enters what is sometimes called the dark era. All black holes have evaporated. All matter has decayed or been emitted as radiation. The universe contains nothing but an extremely dilute gas of photons and other particles, spread across a space that has expanded to unimaginable size at a temperature that is effectively zero, with no structures, no gradients, no sources of energy. This is the heat death, the state of maximum entropy. The state in which no further work can be extracted from the system, no further organization can occur. Nothing can happen, not because everything is frozen, but because there is no gradient left, no hot region and cold region, no high energy and low energy, no cause that can produce a distinguishable effect. The universe does not end, it persists, but it has stopped in the sense that matters. And all through the stelliferous era, the degenerate era, the black hole era, the dark era, the vacuum energy continues to exist. The expansion continues to accelerate. Space continues to grow. The dark energy outlasts everything. Chapter 7, the question that cannot be answered yet. Here is the thing I want you to sit with. We have observed an acceleration. We have named what causes it dark energy, the cosmological constant, the energy of the vacuum. We have modeled it. We have made predictions from it. Those predictions match the data. And we cannot explain it. Not in the fundamental sense of explaining, not in the sense of deriving it from deeper principles, understanding why the number is what it is, connecting it to the quantum fields that fill the vacuum with their zero-point energy. We observe 10 to the negative 9 joules per cubic meter. We calculate 10 to the 113 joules per cubic meter. These should be the same number if dark energy is vacuum energy. They are not. They are 122 orders of magnitude apart. Something is canceling almost all of the vacuum energy, not quite all of it. A tiny fraction remains, and that tiny fraction is what we observe as dark energy, but almost all of it is canceled somehow by something. What? The most elegant possibility historically was supersymmetry, but supersymmetry, if it exists, is broken. The cancellation is incomplete, and the degree to which it is incomplete, the residual vacuum energy after the supersymmetric cancellation, is not naturally small. Getting the residual to be as small as the cosmological constant still requires an extraordinary fine-tuning. Another possibility is that quantum gravity, the theory of gravity at the quantum level, which we do not yet have, naturally constrains the vacuum energy. In general relativity, the vacuum energy has a specific effect. It curves spacetime. In quantum gravity, perhaps there is a constraint, a consistency condition that forces the vacuum energy to be small. The idea goes by various names: the string landscape, the asymptotic safety program, holographic ideas about the nature of spacetime. None of them currently gives a clear, compelling derivation of the cosmological constant. There's also the possibility that the cosmological constant is not truly constant, that what we observe as dark energy is a dynamic field, slowly evolving, that happens to currently have a very small value. This is the quintessence idea. In quintessence models, the dark energy field rolls down a very gently sloped potential, like a ball on an almost flat surface. At early times, the field was in a different configuration. Now it has settled near the bottom. In the future, it will settle further, perhaps approaching zero, perhaps oscillating. If dark energy is quintessence rather than a true cosmological constant, its behavior over time will differ slightly from the cosmological constant prediction. Future surveys, Euclid, Daisy, the Rubin Observatory, may be sensitive enough to detect these differences. If they find that the dark energy density is slightly different than what the cosmological constant predicts, or if they find that it varies slightly with direction, that would be evidence for quintessence. And if it is quintessence, the far future of the universe changes. A quintessence field that rolls to zero means the acceleration eventually stops. The universe reverts to decelerating expansion, eventually becoming static or perhaps recollapsing. A quintessence field that grows, whose potential is such that the field accelerates as it rolls, produces a big rip. A future in which the dark energy becomes so large that it overcomes the gravitational binding of galaxies, then star systems, then individual stars, then planets, then molecules, then atoms, ripping apart every structure in existence in the final moments. We do not know which of these is the true future. The data are consistent with a constant, but the precision is not yet good enough to rule out slow evolution. We are, in a very literal sense, waiting for more data. Chapter 8: Alternative Explanations and the Shape of Ignorance. When a theory makes a wrong prediction, especially a wrong prediction by a factor of 10 to the 122, the natural scientific response is to look for a better theory. The challenge with the cosmological constant problem is that the theories we have are so good for almost everything else that the wrongness is mysterious. Quantum field theory is not a rough approximation. It is precise to extraordinary depths. General relativity is not a sketch. It has passed every experimental test for more than a century. And yet they disagree with each other on this question in the most extreme way possible. This suggests that the solution, when we find it, will be something genuinely new, not a small correction to existing theory, a conceptually new idea. Here are some of the directions active research is pursuing. The first is the landscape of string theory. String theory, or more precisely, superstring theory and its generalization M-theory, is a framework that attempts to unify quantum mechanics and general relativity by positing that the fundamental objects of nature are not point particles but tiny vibrating strings of energy. Different vibrational modes of the string correspond to different particles. Gravity arises naturally from one particular mode, the graviton. String theory has a peculiar feature. It contains an enormous number of possible solutions. Not one unique universe, but something like 10 to the 500 distinct configurations, each with different physical laws, different particles, different constants, including different values of the cosmological constant. This collection of solutions is called the string landscape. And the string landscape, combined with the concept of eternal inflation, a process by which the very early universe may have spawned a vast number of causally disconnected regions, each settling into a different configuration, suggests a physical realization of the multiverse. Most of those regions would have large cosmological constants and no structure. A few would have small cosmological constants and allow stars and planets and observers. We live in one of those few. This is the anthropic reasoning applied to string theory, and it is genuinely controversial. Some physicists find it compelling. It is at least a consistent picture, and it predicts that the cosmological constant should be small, just not zero. Others find it deeply unsatisfying. It makes no unique predictions, explains nothing dynamically, and amounts to a reason why we cannot calculate the cosmological constant from first principles. The debate is not fully resolved. The string landscape is real in the sense that string theory genuinely has this enormous collection of solutions. Whether those solutions correspond to real physical universes is a much deeper question. The second direction is asymptotic safety. This approach tries to make quantum gravity consistent without introducing new fundamental objects like strings. The idea is that gravity is a quantum field theory, but a non-perturbative one. It does not break down at high energies, but instead approaches a fixed point, a scale-invariant regime where the theory is well defined. In asymptotic safety, you can calculate quantum corrections to the cosmological constant, and some researchers claim the calculation gives a naturally small value. This is an active research program, but it is not yet fully developed to the point of making definitive predictions. The third direction is holographic principles. Holography in physics refers to the idea, emerging from studies of black holes and string theory, that the information content of a volume of space is encoded on its boundary surface, not in the bulk. This is counterintuitive. A region of three-dimensional space in this picture is fully described by a two-dimensional surface. The bulk is, in some sense, redundant. Holography is correct, and there are strong theoretical arguments that it is, particularly in spaces with a certain type of geometry called anti-de Sitter space. Then it changes how you think about the vacuum energy. The vacuum energy in the bulk corresponds to something on the boundary. The small value we observe might correspond to something natural and well understood on the boundary. Some researchers have claimed to derive the value of the cosmological constant from holographic arguments. These derivations are not yet fully convincing to the broader community, but the direction is promising. The fourth direction is something called emergent gravity. In emergent gravity theories, gravity is not a fundamental force. It is a statistical effect, an entropic force, that emerges from the thermodynamic behavior of some more fundamental degrees of freedom that we have not yet identified. Just as pressure and temperature emerge from the statistical behavior of molecules that do not themselves have pressure or temperature, gravity might emerge from the behavior of something deeper. If gravity is emergent, the concept of the vacuum energy as a source of gravity takes on a different meaning. Perhaps the reason the vacuum energy does not gravitate as strongly as the calculation suggests is that the connection between vacuum energy and gravity is not what we think. Perhaps in the emergent picture, most of the vacuum energy simply does not couple to the gravitational mode in the way our current equations assume. None of these directions has yet produced a convincing, complete, fully tested explanation of the cosmological constant problem. They are research programs, not answers, but they suggest the shape of the ignorance. We are probably missing a deep conceptual piece, something about the relationship between quantum mechanics and spacetime that we have not yet grasped. And finding it will require, at minimum, a better theory of quantum gravity, which we do not have. The cosmological constant problem is not just a puzzle, it is a boundary marker. It is the place where our current understanding of physics breaks down most visibly and most embarrassingly. And the next great theory of physics, whatever it turns out to be, will probably be born in the space between 10 to the 113 and 10 to the negative 9. Chapter 9, The Personal Scale of the Vacuum. I want to bring all of this closer. Because so far we have been talking about cosmic distances, astronomical energies, timescales that exceed the current age of the universe by factors of trillions. These are the scales on which dark energy operates. These are the scales on which the discrepancy between theory and observation is measured. But the vacuum is not just out there. It is in here. The quantum vacuum, the ground state of the quantum fields, exists everywhere. Not just in the deep intergalactic medium, not just in the cold voids between galaxy filaments. Everywhere, inside your body, between the atoms of your cells, in the nucleus of every atom in your hand, in the space between electrons and quarks, everywhere that space exists, the quantum vacuum exists. And everywhere the quantum vacuum exists, the zero-point energy of the quantum fields is present. You cannot feel it, you cannot measure it by any means available to you. It does not warm you, does not exert a pressure you can sense, does not react with your chemistry in any way that is perceptible, but it is there. And here is the specific thing I want you to sit with. The cosmological constant, the number that describes the energy density of the vacuum and drives the acceleration of the universe, is the same everywhere in space, including inside you. If the vacuum energy density is 10 to the negative 9 joules per cubic meter in the void between galaxies, it is also 10 to the negative 9 joules per cubic meter inside your lungs, inside your cells, inside the spaces that your atoms create by merely existing without being perfectly packed. The same field, the same constant, the same energy. The force that is pushing the Milky Way and Andromeda's neighboring galaxies over the cosmic event horizon, slowly, imperceptibly, on timescales of hundreds of billions of years, is the same kind of energy that is present between your fingers right now. Dark energy does not work on you directly. On the scale of a human body, gravity is overwhelming. The gravitational binding of your cells is a trillion times stronger than the dark energy pushing them apart. Your body will never be torn apart by dark energy. You will not feel the push. You will not notice it. But it is there. And that is a strange kind of intimacy. You are not merely observing a cosmic force from a safe distance. You are inside it. It is inside you. the field that is eating the universe, the vacuum energy that will eventually empty the sky and drive all structure into silence, occupies the same space that you do, right now, always. This does not require mysticism. It does not require metaphor. It is just true. The cosmological constant applies everywhere space exists. You exist in space. The cosmological constant applies to you. And the reason it does not affect you, the reason you are here, intact, thinking about all of this, is that on your scale, the other forces are far stronger. Gravity binds your cells together with a force that dark energy cannot overcome at these distances. Electromagnetism binds your molecules. The strong nuclear force binds your nuclei. All of these are so much stronger than dark energy on small scales that dark energy is effectively irrelevant to everything you will ever experience. But if you scaled up, if you took all the matter in your body and spread it over a sphere 10 million light years across, the balance would change. At that scale, dark energy would start to matter. The repulsion would become comparable to the gravity. And if you scaled up further to the scales of galaxy clusters and cosmic filaments, dark energy wins. It is the dominant force on those scales. The forces of nature have different ranges and different dependencies on distance. Gravity falls off as the square of distance, just as dark energy's repulsion grows proportional to distance. At small scales, gravity always wins. At large scales, dark energy always wins. The crossover point is the scale of galaxy clusters, roughly 10 to 100 million light years. Below that, gravity rules, structures persist. Above it, dark energy rules, structures disperse. You are, by an enormous margin, on the gravity side of this boundary. But the dark energy is still there. Chapter 10, The Stability of the Ground. Now I want to take you to one more place, somewhere quieter and more unsettling. We have been assuming throughout this discussion that the vacuum we live in is the true vacuum, the real ground state, the actual lowest energy configuration of the quantum fields. But we do not know this. Quantum field theory allows for a situation called a false vacuum. A false vacuum is a configuration of the fields that appears locally to be a minimum, a stable resting point, but is not the global minimum. It is analogous to a ball resting in a hollow on the side of a hill. The ball is stable in the sense that small perturbations will not push it out of the hollow. It appears locally to be at rest, but it is not at the bottom of the hill. There is a lower energy state available. In quantum mechanics and quantum field theory is a quantum theory, there is a process called quantum tunneling by which a system can transition from a higher energy state to a lower energy state even without enough classical energy to cross the barrier between them. Tunneling is the mechanism that makes nuclear fusion in the sun possible. Protons get close enough to fuse because they tunnel through the repulsive barrier. Tunneling is the mechanism behind radioactive alpha decay. It is a real process observed countless times. If our vacuum is a false vacuum, tunneling can occur, not often, not predictably in location or time, but somewhere at some moment the quantum fields could tunnel from their current configuration, the one we call our vacuum, to a lower energy configuration, a true vacuum if one exists. When this happens, a bubble of true vacuum would form. Inside the bubble, the fields are in the lower energy state. The laws of physics inside the bubble would be different. The fundamental constants would be different. The masses of particles, the strengths of forces, the value of the cosmological constant, all different. What kind of chemistry or physics, if any, would be possible inside such a bubble, we do not know. The bubble wall, the boundary between the false vacuum and the true vacuum, would expand outward at the speed of light. It carries with it the transition to the new physics. Everything the bubble wall passes through is transformed, atoms restructured, nuclei dissolved, or simply rendered into configurations that do not support any of the structures we know. There would be no warning, there could be no warning because no signal can travel faster than the speed of light, and the bubble wall travels at the speed of light. The first you would know of it would be its arrival, and by then, in less than a Planck time, 10 to the negative 44 seconds, the transition would be complete. This is vacuum decay. Is it likely to happen? Almost certainly not on any human timescale or any stellar timescale. If our vacuum were highly metastable, the universe would not have lasted 14 billion years without decaying. The very existence of the universe in its current form is evidence that the vacuum is either stable or very long-lived. What does very long-lived mean? Calculations based on current measurements of the Higgs boson mass and top quark mass suggest that if our vacuum is metastable, the tunneling rate is so slow that the expected time before a tunneling event occurs somewhere in our observable universe is something like 10 to the 500 years. That is a number so large that even the full timeline from the Big Bang to the heat death of the universe would be a negligible fraction of it. So the danger, if danger is even the right word, is not imminent. It is not imminent in any timescale that biology or civilization or even stellar evolution could be said to operate on. But it is not excluded. And I find that curious, not terrifying. The timescales make terror disproportionate, but genuinely strange. The ground we stand on at the deepest level might not be the true ground. The lowest floor of the building might not be the basement. There might be a sub-basement, inaccessible except by the most extreme quantum tunneling, and if something reaches it, the building above does not survive the descent. We live possibly on a ledge, an extraordinarily stable ledge, a ledge so stable that we will never, not in any lifetime we can imagine, fall from it. But a ledge, and the only thing preventing the fall is the height of the quantum barrier between where we are and where the fields could go. We cannot measure that barrier with certainty. We can estimate it. The estimates say we are safe, but estimates are not proofs. Chapter 11: What the measurements cannot reach. There is a particular kind of knowledge that science generates and a particular kind that it cannot reach. The distinction matters here. Science can tell us the value of the cosmological constant. It has done so with increasing precision. The current measurement sits at roughly 2.24 times 10 to the negative 3 electron volts to the fourth power, which in more natural cosmological units corresponds to the energy density we have been discussing. Future measurements from Euclid, from the Vera Rubin Observatory, from the Nancy Grace Roman Space Telescope will improve this precision. What science cannot currently tell us is why this value is what it is. The measurement gives us the number. The theory cannot explain the number. That gap between the measured value and the calculated value, between what we observe and what we can derive, is the precise shape of our ignorance. This is not unusual in the history of physics. Every era has had measurements it could not explain. In the late 19th century, the spectrum of light emitted by hot objects, called blackbody radiation, could not be explained by classical physics. The calculation gave an infinite answer at high frequencies, which physicists of the day called the ultraviolet catastrophe. Max Planck solved it in 1900 by introducing the quantum hypothesis, the idea that energy comes in discrete packets. The solution required a new concept, not a patch on existing theory, a new piece. In the early 20th century, the photoelectric effect, the way light ejects electrons from metals, could not be explained by the classical theory of light. Einstein explained it in 1905 by arguing that light is quantized into photons. Again, a new concept was required. In the 1930s, the stability of the atom, why electrons do not spiral into the nucleus and release all their energy as radiation, could not be explained by classical electrodynamics. Quantum mechanics provided the answer. Each time, the unexplained measurement was not a small discrepancy. It was not a rounding error. It was a signal that something fundamental was missing from the conceptual toolkit. The cosmological constant problem is, by this standard, the loudest signal in the history of physics. A discrepancy of 10 to the 122 is not asking for a small correction. It is asking for a revolution. And revolutions in physics do not come on schedule. They come when someone sees something differently, when a new framework arrives that makes the old measurements look natural rather than mysterious, when the shape of the problem changes because the shape of the concepts around it changes. We are waiting for that framework. It will probably require reconciling quantum mechanics and general relativity in a way that changes how we think about the vacuum, about space, about what it means for something to have energy. It may require new ideas about the relationship between information and geometry. It may require a different understanding of what time is, or what boundaries between theories mean. We do not know, and the not knowing is not a failure, it is the frontier. Every generation of scientists has had a frontier that seemed impenetrable from where they stood, and every generation was eventually succeeded by people who penetrated it, not always by being smarter, often by having access to new data, new tools, new mathematical languages that made the problem tractable in ways it had not been before. The cosmological constant problem has been recognized as a problem since the 1970s. It has resisted solution for 50 years. That is a long time, but not an unusually long time in physics. The problem of understanding the behavior of superconductors at the microscopic level took decades. The unification of electricity and magnetism took most of the 19th century. The explanation of the perihelion precession of Mercury, a tiny discrepancy in orbital mechanics, waited 100 years for general relativity. The solution will come, the question is only what form it will take. And perhaps the most remarkable thing is that we know precisely where the answer needs to come from. We know the exact number that needs to be explained. We know the exact discrepancy. The signal is sharp and clear and documented. We just do not yet know how to read it. Chapter 12, the gift of this moment. Let me come back from the far future and the deep theory and talk about now. This specific moment, the universe as it is tonight. We are approximately 13.8 billion years into the story. Stars have been burning for 13.7 billion of those years. The universe is full, an extraordinary fullness by the standards of its own future, with roughly 2 trillion galaxies. Most of them we cannot even name. We have cataloged a small fraction. We have imaged a tinier fraction. The rest are points of light in the deep surveys, or smears in the noise, or beyond the reach of our instruments entirely. The observable universe extends roughly 46 billion light-years in every direction, not because that is how far light has traveled since the Big Bang, that would be 13.8 billion light-years, but because space itself has been expanding while the light traveled, stretching the distance to the original sources. The edge of what we can see is defined by the surface of last scattering, the moment, roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and the light was released. That light has been traveling ever since, and we detect it now as the cosmic microwave background, a faint, almost perfectly uniform glow in every direction, the afterglow of the universe's infancy. We can see simultaneously the oldest light and the nearest light. The cosmic microwave background from 13.8 billion years ago, and the light from the moon a little over a second old. We can see galaxies that have been forming stars for 10 billion years and galaxies that formed stars for only a few 100 million years and then went quiet. We can see the early universe and the evolved universe stretched out like a geological record in the rock of the sky. This window, this extraordinary archive of cosmic history, is available right now. It will not always be. As the expansion accelerates, as dark energy continues its patient work, the horizon shrinks. The oldest light, the cosmic microwave background, will redshift into invisibility. The distant galaxies will cross the horizon. The sky will empty. In 100 billion years, the cosmic microwave background will have redshifted to wavelengths so long that it will be undetectable with any antenna of conceivable size. The signal will be gone. A civilization living then will have no direct access to the oldest light. In a few 100 billion years, only the local group will remain visible. The 2 trillion galaxies of the current observable universe will all have crossed the horizon. The only objects in the sky will be the stars of what was once the Milky Way and Andromeda, now merged into Milkomeda, and the satellite galaxies gravitationally bound to that system. Future civilizations, if they exist, if they have developed science, will look at the sky and see a single large galaxy surrounded by darkness. They will measure its stars, its chemistry, its dynamics. They will discover that physics works the same as we know it. They will deduce that the universe had a beginning, but they will have no direct observational evidence for the scale and structure of the universe beyond their local group. They will have to take it on faith, or derive it from theoretical arguments, or find some indirect evidence, perhaps subtle features of the cosmic gravitational wave background, which may be detectable long after photon radiation has faded. We live in the era when the evidence is direct, when you can look up and see it. And I find that genuinely moving, not in a sentimental way, in a specific, factual way. The universe tonight is the most accessible it will ever be to a being with our kind of instruments and our kind of eyes. The archive is open. The records are readable. The history is inscribed in the light. Go outside on a clear night away from city lights, lie on your back on the ground and look up. The Milky Way, if you can see it, is a band of light made up of hundreds of billions of individual stars so close together at this distance that the light blurs into a river. It is not a painting. It is not a metaphor. It is hundreds of billions of suns. The Andromeda galaxy, visible as a faint smear in the constellation Andromeda, is 2.5 million light-years away. The light you see left it 2.5 million years ago, when Homo erectus was beginning to master fire on the African savanna. That light has been traveling toward you for your entire species' existence, and tonight it arrives. The Magellanic Clouds, visible from the southern hemisphere, are satellite galaxies of the Milky Way, small, irregular, containing hundreds of millions of stars, close enough to be resolved by the naked eye as distinct blobs of light rather than points. And behind all of them, beyond the reach of any naked eye but not beyond the reach of physics, are the billions of galaxies of the deep universe, each one a complete ecosystem of stars and dust and dark matter, each one separated from us by distances measured in billions of light years, each one carrying in its light the imprint of its own history. All of this is accessible right now, tonight. It will not be accessible forever. Dark energy is working, the expansion is accelerating, the horizon is closing. We have a window. Chapter 13, The Field and the Failing. I want to end with something that is harder to say precisely but feels, to me, worth saying. There's a field in the vacuum of space that we do not understand. It is everywhere. It has a precise, measured value. That value is consistent with being the cosmological constant that Einstein introduced and discarded and that observations have vindicated. It is causing the universe to expand faster over time. It will eventually empty the sky. It is the dominant energy in the universe. And we cannot explain it. We have names for it, we have measurements, we have theoretical frameworks that include it, but we cannot derive it. We cannot predict it from first principles. We cannot show why it is what it is. And yet it made this possible. If the vacuum energy were 100 times larger, gravity could not have formed galaxies. If it were 100 times smaller or negative, the universe would have recollapsed. If it were exactly zero, the expansion would have coasted and the universe would be here, but it would be a different kind of here. The value we have small, positive, astonishingly precisely small relative to the theoretical prediction, is the one value that permits a universe of long-lived stars and stable planetary systems and the slow, patient emergence of complexity. Not because the universe was trying to produce complexity. The universe was not trying to do anything, but the value it has is the one in which complexity happened, and we are part of that complexity. There is something quietly vertiginous about that if you let yourself feel it. Not the fear that comes from scale, not the insignificance of a small creature in a vast cosmos. That is a real experience, but it is not what I am pointing to, something else. The specific strangeness of being a consequence of a constant you cannot explain, of existing because a number has a value that nobody knows how to derive. Of looking up at a sky full of light and knowing that the light is reaching you because, somewhere in the equations, a term that should be huge is almost zero, and nobody knows why. There's a generosity in that, not the generosity of intention. Again, the universe intends nothing but the generosity of outcome. The universe did not have to produce beings who ask questions about it. The physics that causes galaxies to form does not require that any of them produce minds, and yet here we are, asking. The vacuum is not empty, the expansion is accelerating, the horizon is closing. The mathematics contains a number that does not fit, and in that gap a new physics is waiting. And you are in the middle of it, not as a spectator, as a part of it, as one of the structures that the right cosmological constant permitted to exist, as one of the patterns of matter and energy complex enough to wonder about the constants that made it possible. The field is everywhere, inside the room you are in, inside the air, inside the silence between one thought and the next. It is doing its quiet work and has been for as long as the universe has existed and will continue to do so for longer than we can easily imagine. You will not feel it, you will not detect it with any instrument you carry. But it is there, and it is the reason in a very specific causal chain that you are here to notice the silence. That is the field. That is what is eating the universe. And for now, for this specific slice of cosmic history, this window that is open tonight and slowly, imperceptibly beginning to close, the sky is full. Go look at it. Chapter 14, What Cosmological Surveys Are Actually Teaching Us. The era of precision cosmology, the ability to measure the parameters of the universe to a few percent or better, is very young. It is, in the sweep of scientific history, an infant. The first precise measurement of the cosmological constant came from the supernova surveys of 1998. At that point, the uncertainty on the value was large, 30 or 40%. The data were consistent with a cosmological constant, but also with a slowly evolving dark energy that looked similar at the current epoch. You could not yet distinguish between a true constant and a slowly rolling field. In the 2.5 decades since, the precision has improved dramatically. The Planck satellite, launched in 2009 and operating until 2018, mapped the cosmic microwave background to extraordinary detail. By measuring the tiny temperature fluctuations in the CMB, fluctuations on the level of 1 part in 100,000, Planck extracted the cosmological parameters with percent-level precision. The dark energy density, the matter density, the spatial curvature of the universe, the rate of expansion at various times. All of these were pinned down with a precision that would have seemed fantastical to cosmologists of a generation earlier. The results were consistent with what is called the lambda-CDM model, lambda for the cosmological constant, CDM for cold dark matter. A universe containing roughly 5% ordinary matter, 27% dark matter, and 68% dark energy, expanding from an initial hot, dense state with a geometry that is spatially flat to high precision. This model fits an extraordinary range of observations, not just the CMB, but the large-scale distribution of galaxies, the abundance of light elements produced in the first minutes after the Big Bang, the distance-redshift relationship of type Ia supernovae. Lambda CDM is not just consistent with a few data sets. It is consistent with everything we have measured. It is sometimes called the standard model of cosmology. But like all standard models, it has tensions. The most notable tension is a discrepancy called the Hubble tension. The Hubble constant, the current rate of expansion of the universe, can be measured in two independent ways. One way is through the early universe. Using the CMB and the physics of the first few 100,000 years after the Big Bang, you can extrapolate forward to predict the current expansion rate. Planck and other CMB experiments give a value of roughly 67 to 68 kilometers per second per megaparsec. The other way is through the late universe. Using distance ladders built from Cepheid variable stars, type Ia supernovae, and other standard candles, you can measure the expansion rate directly in the local universe. Multiple groups using this method get values around 73 to 74 kilometers per second per megaparsec. These two measurements disagree, not by a lot in absolute terms, 6 or 7 kilometers per second per megaparsec, but by enough given the precision of both measurements to be statistically significant. The discrepancy is now at roughly 5 sigma, the level at which in particle physics a discovery is declared. Both measurements appear to be correct. Their uncertainties have been carefully checked, and yet they give different answers. This is the Hubble tension, and it is currently the most active controversy in observational cosmology. Why does it matter for dark energy? Because one possible resolution is that dark energy is not a constant. If the dark energy density was different in the early universe than it is now, higher in the early universe perhaps, it would change the physics of the CMB epoch and produce a different prediction for the current expansion rate. This is called early dark energy, and it is an active area of theoretical research. Early dark energy models posit that there was an additional component of dark energy in the early universe, with an energy density that was significant at the time of matter-radiation equality and then diluted away. The idea is that this early dark energy increased the expansion rate of the early universe slightly, changing the acoustic oscillations in the CMB in a way that, when the data are analyzed, gives a higher Hubble constant. The models are not perfect. They introduce new parameters and new fine-tuning problems of their own, but they illustrate the key point. The Hubble tension is not merely a measurement problem. It may be evidence that our picture of dark energy is incomplete, that what we think of as a constant has in fact had different values or played different roles at different epochs. The Dark Energy Spectroscopic Instrument, DESI, produced its first major results in 2024. DESI is a facility at the Kitt Peak National Observatory in Arizona, equipped with 5,000 robotically positioned optical fibers that can simultaneously measure the spectra of 5,000 galaxies. Over 5 years of operation, it will measure the spectra of roughly 40 million galaxies and quasars across a redshift range that covers the last 11 billion years of cosmic history. From these spectra, DESI extracts the redshift of each galaxy, how much its light has been stretched by the expansion, and from the redshift its distance and recession speed. By mapping this three-dimensional distribution of galaxies, DESI can measure a feature called baryon acoustic oscillations, a preferred scale in the clustering of matter, imprinted when sound waves froze in the early universe and visible today as a slight excess of galaxy pairs separated by roughly 500 million light-years. This scale acts as a standard ruler. You know its physical size from theory. You measure its apparent size at different redshifts, and from the comparison, you extract how the expansion rate has changed over time, which tells you about dark energy. The DAISY Year 1 results, released in 2024, showed something interesting. When fitting models to the data preferred a dark energy equation of state that was slightly different from a cosmological constant, specifically, an equation of state that might be slowly evolving with time. The result was not definitive. The statistical significance was not yet at the level of a confident detection of dark energy evolution, but it was intriguing. It was consistent with either a true cosmological constant or a slowly evolving dark energy, with the evolving dark energy being slightly preferred. Future DAISY data releases, the full 5-year survey, combined with data from Euclid and the Rubin Observatory, will sharpen these constraints dramatically. If the trend continues and strengthens, it will be the first direct evidence that dark energy is dynamic rather than constant, a revolution in cosmology. If the data converge on a constant instead, it will reinforce the cosmological constant picture and deepen the question of why that particular value. Either way, the field is active, the measurements are improving, we are not done. Chapter 15, The Vacuum at the Edge of What We Know. Let me take you to a place that is genuinely at the edge of what is known, not the edge of the observable universe, but the edge of theoretical physics. The place where the known frameworks break down and the unknown begins. This place is sometimes called the Planck scale. It is defined not by a geographical location, but by a combination of fundamental constants, the speed of light, Planck's constant, and Newton's gravitational constant. Combined in the right way, these constants define a fundamental unit of energy, length, and time. The Planck length is approximately 1.6 times 10 to the negative 35 meters. This is incomprehensibly small. A proton is roughly 10 to the negative 15 meters across. The Planck length is 10 to the negative 35 meters, 20 orders of magnitude smaller than a proton. To zoom into a proton by the same factor as a proton to the Planck length, you would need to zoom into every atom 20 times over, each time revealing a substructure 20 times smaller than the previous. At the Planck scale, our current theories, quantum mechanics and general relativity, are both required simultaneously and known to be incompatible. Quantum mechanics says the vacuum fluctuates. General relativity says spacetime curves in response to energy. At the Planck scale, the quantum fluctuations of the vacuum would be so energetic that they would create spacetime curvatures of order 1. The fabric of spacetime itself would fluctuate, wrinkle, and fold on those scales. Our equations cannot handle this. They give nonsensical answers. This is why the Planck scale is the natural cutoff for calculating the vacuum energy. Below the Planck scale, we trust our theories. Above the Planck scale, we trust them less and less. At the Planck scale, we trust them not at all. What actually happens at the Planck scale is unknown. We have candidate theories, string theory, loop quantum gravity, causal dynamical triangulations, asymptotic safety, each offering a different picture of what spacetime looks like at those scales. But none of them has made a unique, testable prediction that has been confirmed by experiment. They remain mathematical frameworks awaiting empirical contact. The challenge is that the Planck scale is so far beyond the reach of current experiments that accessing it directly seems impossible in the foreseeable future. The Large Hadron Collider probes energies of a few TeV, a few thousand times the rest mass of a proton. The Planck scale corresponds to energies roughly 10 to the 15 times higher. A particle accelerator capable of reaching Planck energies would, by naive extrapolation from current technology, need to be the size of the solar system or larger. This does not mean we learn nothing about Planck-scale physics. Indirect evidence can come from cosmology. The very early universe was at Planck densities, and the patterns it produced are imprinted in the large-scale structure we observe today. Gravitational wave astronomy may eventually probe quantum gravitational effects. Astronomical observations may catch signals from processes near the Planck scale through gamma-ray bursts or other extreme events. But the vacuum energy, the most direct confrontation between quantum mechanics and gravity, remains the most glaring symptom of our ignorance about the Planck scale. The answer to the cosmological constant problem, when it comes, will almost certainly come with a theory of quantum gravity. The two problems are deeply linked. Understanding what the vacuum actually is at the Planck scale will tell us why its energy has the value it has at the scale of the cosmos. We are waiting, in other words, for a theory that begins at the smallest imaginable scale and reaches all the way up to the largest. A theory that connects the Planck length to the observable universe. A theory that explains why the number that describes the ground state energy of the quantum fields equals, to extraordinary precision, the number that describes the acceleration of the expansion of the cosmos. That theory does not yet exist. Its existence would arguably be the greatest intellectual achievement in the history of science. And the measurement that will most constrain it, the cosmological constant, is already known. Chapter 16, Why any of this should matter to you. I want to be honest about something before I finish. Everything I have described in this video is true in the sense that it reflects the current best understanding of physics and cosmology. The vacuum energy is real. The acceleration of the universe is real. The Casimir effect is real. The discrepancy between the predicted and observed vacuum energy is real. The far future timeline, with its caveats about theoretical uncertainty, is based on real calculations. But why should any of this matter to you? Not in a cosmic sense. I know the cosmic argument for why these things matter. The universe is large, complex, and strange, and understanding it is intrinsically valuable. I believe that, but I want to be more specific. Why should you, lying in bed at 2 in the morning with the window dark and the room quiet, care about the energy of the quantum vacuum? Here is my answer. Because it changes the quality of your attention. Not in a mystical way, not because knowing about dark energy will change how you feel about your life or what decisions you make tomorrow or whether you get enough sleep. It probably will not in any direct sense. But it changes what you are attending to when you attend to the ordinary. The space in this room, the space around you right now, is not empty. You knew that in the sense that air is here, but now you know it in a different sense. The ground state of reality is not silence. It is a particular kind of activity, a particular kind of quantum noise that cannot be reduced and cannot be stilled and carries within it the same physics that will ultimately dismantle the large-scale structure of the observable universe. The room you are in and the space between galaxy superclusters are subject to the same cosmological constant. The same physics applies at both scales, even if the practical consequences differ by 122 orders of magnitude. And the fact that we do not know why, that the number that governs the most important force operating on cosmic scales is one we can measure but not derive, is a genuine open wound in physics. A wound that has been open for 50 years, that some of the most brilliant scientists of the last century have examined from every angle, and that has not yet healed. That wound is an invitation, not necessarily to you. Most of us will not become theoretical physicists, and the wound will probably not be closed by a lone thinker working in isolation, but by a community of researchers with access to better data and better mathematical tools. but the fact that the wound exists, that the question is open, that the most fundamental properties of the thing you are embedded in are not yet understood, that is worth knowing. Because it puts your own not knowing in company. You lie awake at night wondering about things you do not understand, about what happens to consciousness after death, or whether meaning exists, or what your life adds up to, or whether the choices you are making are the right ones. These questions are not answered by physics, and I am not suggesting they are. But the not knowing itself, the genuine confrontation with a question that matters and has no currently available answer, is something you share with the field, with physicists who have devoted their careers to the cosmological constant and remain unable to explain it, with mathematicians working on frameworks that might someday bridge the gap, with experimenters collecting data from billion-dollar telescopes pointed at galaxies billions of light years away. They are lying awake with their not knowing too. There is a kind of company in that, not comfort exactly, not resolution, but company. And the universe, with its vacuum energy and its cosmic acceleration and its impending emptying of the observable sky, does not care about any of us, does not know about any of us, does not provide comfort or company in any active sense. But we can provide it to each other by understanding what we are embedded in, by knowing that the ground beneath us is not nothing and the sky above us is not permanent, and the science that maps the distance between those two facts is still, genuinely in progress. That seems worth knowing. That seems worth the time it took to lie still and think about it. Chapter 17, The Shape of the Next Answer. Every revolution in physics has had a characteristic shape. Newton's revolution unified the motion of objects on Earth with the motion of objects in the sky. Before Newton, the planets moved according to one set of rules and falling apples according to another. After Newton, they moved according to the same rule. The great conceptual move was to see that these apparently different phenomena were instances of the same thing. Maxwell's revolution unified electricity, magnetism, and light. Before Maxwell, these were three separate topics. After Maxwell, they were one. Electric fields and magnetic fields were aspects of the same electromagnetic field. Light was an electromagnetic wave. The great conceptual move was to see that three separate structures were in fact one. Einstein's first revolution, special relativity, unified space and time. Before Einstein, space was three-dimensional and time was separate. After Einstein, they were aspects of a single four-dimensional space-time, and their separation depended on who was measuring. His second revolution, general relativity, unified gravity with geometry. Before general relativity, gravity was a force acting through space. After general relativity, gravity was the curvature of space-time. The great conceptual move was to see that a force and a geometry were the same thing. The quantum revolution unified matter and energy, particles and waves. Before quantum mechanics, an electron was a particle and light was a wave. After quantum mechanics, everything was a quantum field and particles were excitations. The great conceptual move was to see that the particle-wave distinction was an artifact of the scale at which you were looking, not a fundamental divide. What is the shape of the next revolution? It will probably unify quantum mechanics and general relativity. It will probably change how we think about spacetime at the Planck scale, and it will probably, as a byproduct, explain the value of the cosmological constant. The characteristic move of the next revolution, the thing that will look obvious in hindsight, might be something like this. Seeing that the energy of the vacuum and the geometry of spacetime are aspects of the same thing, in the same way that Maxwell saw that electricity and magnetism were aspects of the same thing. Right now we treat them separately. The vacuum energy in quantum field theory is calculated without reference to spacetime geometry. The spacetime geometry in general relativity responds to all forms of energy, including the vacuum. The two theories hand information to each other across a poorly understood interface. The next revolution might dissolve that interface, might show that what we call vacuum energy and what we call spacetime curvature are two descriptions of the same underlying structure, and that the apparent discrepancy between the calculated vacuum energy and the observed cosmological constant dissolves when you use the right description. This is speculative. I am describing the shape of an answer that has not been found, but the shape of revolutions past is a reasonable guide to the shape of revolutions future. They tend to reveal that apparently separate things are one thing, that apparent contradictions were artifacts of an inadequate description, that a new concept dissolves an old problem. The cosmological constant problem is an old problem. The dissolution that resolves it will be new. We will not find it tonight, probably not this decade, maybe not this generation. But the problem is clear, the measurements are precise, the gap is defined. The next revolution knows where to begin. Chapter 18, The Silence That Comes After. I want to return one last time to the far future, not to dwell on it, but to let it do what it is meant to do. The universe will expand, the dark energy will continue its work, the horizon will close, the sky will empty, the stars will burn out, the black holes will evaporate, the vacuum will remain. You will not be there to see any of it, not because you will die, though you will, but because these timescales are so vast that the concept of individual consciousness or civilization or even species barely registers against them. The end of the stelliferous era is 100 trillion years away. The evaporation of the last supermassive black hole is something like 10 to the 100 years away. These are not timescales you can fear or mourn in the usual emotional sense. They are too large. They exist as numbers, not as feelings. But there is something worth noticing about them. The universe will go on without you, without anyone, for an almost incomprehensibly long time, long after every structure you can identify has dissolved. Long after every galaxy has faded, every star has cooled, every molecule has been broken down by proton decay or quantum tunneling. The vacuum will remain, the expansion will continue, the dark energy will still be there doing its quiet work. And in that future, that dark, cold, structureless, almost eventless future, the cosmological constant will still be the cosmological constant. The vacuum energy will still be what it is. The field that is eating the universe will still be there, unchanged, having eaten it. That constancy is perhaps the strangest thing about dark energy. Everything else changes, matter forms and disperses, stars ignite and die, galaxies merge and evaporate, black holes form and evaporate. The cosmic microwave background redshifts to wavelengths longer than the observable universe. The density of matter falls toward zero. But the vacuum energy stays constant because it is a property of space itself, and space is still there. Space keeps being created by the expansion. Every new cubic meter of space carries the same energy density as the old cubic meters. The cosmological constant does not thin, it does not dilute, it does not decay. The field is patient, more patient than anything we can imagine. It will be doing exactly what it is doing now, expanding space, pushing galaxies apart, maintaining its constant energy density in 10 to the 100 years. In 10 to the 1,000 years, possibly forever. Whether anything else will exist in that distant future to appreciate or fail to appreciate this patience, we do not know. The quiet horror and the quiet majesty of that are two sides of the same thing. What remains? And so, to close, there's a field in empty space that we cannot see and cannot feel and cannot directly detect. It is not a metaphor. It is a measured, quantified, physically real entity that determines the large-scale behavior of the universe. It is driving the expansion of space. It is responsible for the accelerating separation of galaxies. It will, over timescales beyond ordinary human comprehension, determine the ultimate fate of everything. We do not know what it is made of. We do not know why it has the value it has. We know its value to a few percent, and we cannot derive it from any theory we currently have. The gap between what we calculate and what we observe is the largest in the history of science. It is also the best clue we have to the next great theory of physics. It is a field that permeates this room, this moment, this breath. A field that is present in the vacuum between your cells and the vacuum between galaxy clusters. A field that has been there since the earliest epochs of the universe and will be there long after the last black hole has evaporated and the last photon has redshifted beyond any possible detection. And you are here in the middle of it right now, in the window when the sky is still full and the light still reaches us and the archive is still open. The field is doing its work. You are doing yours. Go ahead and rest now. An interlude on dark matter and its difference. I want to pause and draw a distinction that sometimes gets blurred because understanding it clarifies what dark energy actually is by contrast. Dark matter and dark energy are often mentioned in the same breath. They appear together in the lambda CDM model. They are both dark in the sense that they do not emit or absorb light. They both constitute the vast majority of the universe's content, dark matter around 27%, dark energy around 68%. Together, they make up roughly 95% of everything. Ordinary matter, atoms, molecules, the stuff you and everything you have ever seen is made of, constitutes only about 5% of the total energy budget of the universe. But dark matter and dark energy are completely different things. Dark matter is matter, it has mass, it has gravity, it clusters, it forms halos around galaxies and filaments between them. It is cold in the cosmological sense, meaning it moves slowly compared to the speed of light, which is why structures like galaxies can form under its influence. The evidence for dark matter is overwhelming. The rotation curves of galaxies, the dynamics of galaxy clusters, the patterns of the cosmic microwave background, the large-scale structure of the universe. All of these are consistent with a universe that contains a large amount of matter that does not interact with light, but does interact through gravity. What dark matter is, however, we do not know. The leading candidate for decades has been a class of particles called weakly interacting massive particles, WIMPs. These are hypothetical particles that interact with ordinary matter only through gravity and the weak nuclear force. They would have been produced in the hot early universe. Their density would have been set by the balance between production and annihilation, and the resulting abundance would have naturally given something close to the observed dark matter density. The WIMP hypothesis has been tested extensively. Underground experiments, vast tanks of liquid xenon, pure crystals of germanium, facilities deep in mines where the rock shields the detector from cosmic rays, have searched for the occasional collision between a passing dark matter particle and an ordinary atom. So far, nothing convincing has been found. The parameter space available to WIMPs has been dramatically narrowed. Alternative candidates include axions, very light particles motivated by a different theoretical problem, the strong CP problem of quantum chromodynamics, and primordial black holes formed in the early universe before stars and galaxies existed. Whatever dark matter is, it is not dark energy. Dark matter clusters, dark energy does not. Dark matter dilutes as the universe expands. As the same mass occupies a larger volume, the density falls. Dark energy does not dilute, it is a property of space, and as space grows, the dark energy grows with it. This distinction is the key to understanding why dark energy drives the acceleration. In the early universe, dark matter dominated. Its density was enormous. Its gravity decelerated the expansion. But as the universe expanded, the dark matter diluted. The energy density in dark matter fell as 1 over the cube of the scale factor. As the universe doubled in size, the dark matter density fell by a factor of 8. Dark energy density stayed constant. So as dark matter diluted and dark energy did not, there came a point, again, roughly 5 to 6 billion years ago, where dark energy surpassed dark matter in energy density. After that crossing, dark energy dominated. Its repulsive effect overtook the decelerating effect of dark matter. The expansion began to accelerate. We are now in the dark energy-dominated era. Dark matter still matters. It shapes the internal structure of galaxies and galaxy clusters, where the local density is much higher than the cosmic average. But on the largest scales, dark energy wins. Understanding dark matter would not resolve the cosmological constant problem, but it would complete our picture of what the universe is made of. It would close one of the major open questions in physics, while dark energy remains the other. Both are dark, both are unknown, neither is the other. The distinction matters. On consciousness and cosmic questions. There is a question that tends to arise when you spend long enough thinking about the far future and the emptiness it will bring, and I want to address it directly, because I think the way most people address it is slightly off. The question is whether any of this has implications for mining. Whether knowing that the universe will eventually be cold and dark and structureless, whether knowing that every star will go out and every galaxy will fade, and even the black holes will evaporate, changes how we should feel about our lives. The honest answer is probably not, in the direct way the question implies. Our emotional lives are calibrated to the scales we evolved in, the time scale of a human life, of a family, of a civilization. We care about what happens over days and years and generations. We are not biologically equipped to feel anything about what happens in 10 to the 100 years. The irrelevance of cosmic timescales to human emotional life is not a failure of imagination. It is appropriate scaling. Grief about the eventual heat death of the universe is not a more enlightened response than not grieving about it. The universe's far future is simply outside the range of scales at which our emotional systems operate usefully. But there is a subtler form of this question, and it deserves a subtler answer. The question of meaning is sometimes posed as a cosmic one. Does the vastness of the universe or the finitude of its complexity make individual human lives meaningless? And the cosmological answer is that meaning is not a property the universe assigns. The universe does not have opinions about which patterns in it are significant. Stars do not know they are beautiful. Galaxies do not know they are large. The cosmological constant does not know that its value happens to permit the existence of beings who can wonder about it. Meaning, as far as we know, is something that arises in minds, specifically in minds that are capable of representing the relationship between things and caring about it. The meaning of your life is not something that will be erased when the last black hole evaporates. It is not in the universe's records to begin with. It is in your experience, in your relationships, in what you do with the time you have. Cosmology does not threaten meaning, it contextualizes it, which is not the same thing. What cosmology does do, what the specific strangeness of the vacuum energy does, is place your existence in a context that is genuinely strange. You are a pattern of matter sustained by forces that we understand well, embedded in a vacuum that we understand only partially, in a universe that is expanding at an accelerating rate for reasons we cannot derive from first principles. That is the context. It is a strange one, but the strangeness of the context does not reduce the reality of what is in it. You are here, the vacuum is there, the field is pushing, the sky is still full. These are all true at once. And the fact that we can think about all of them simultaneously, that a mind built from ordinary atoms can hold in it the concept of the cosmological constant and the concept of personal meaning and notice the relationship between them, is itself one of the stranger and more remarkable things the universe has produced. Not because it makes us special in some cosmic register. We are not. We are very small, very brief, very local. But the noticing is real. The experience of these questions is real. And the universe, in producing the conditions in which those experiences could occur, did something that is genuinely unusual in the history of matter and energy. It made something that could look back and ask, and not yet know the answer. That is enough for now. That is perhaps enough for always. A note on the numbers we cannot yet read. There is a specific kind of wonder that belongs to standing at the edge of what is known, looking out at what is not. It is different from the wonder of looking at a beautiful thing. A sunset is beautiful, and you can take in the whole of it, and it is what it appears to be. The wonder of the cosmological constant is different. It is the wonder of a question that is fully formed, precisely posed, precisely measured, but not yet answered. We know the question, why is the vacuum energy 10 to the negative 9 joules per cubic meter rather than 10 to the 113? We know the measurement, we know the theoretical calculation, we know the gap. What we do not know is the principle that closes it. And that particular kind of not knowing, the kind where the question is sharp and the measurement is precise and the gap is defined to many decimal places, is a different experience than the vague not knowing of wondering what happens after death or whether there is a purpose to existence. Those questions may not have scientific answers. The cosmological constant question does. It is answerable, completely and precisely answerable in principle by the right theory applied to the right data. We just do not have the right theory yet. That is why the wonder of the cosmological constant is a forward-pointing wonder, not a mystery in the sense of something permanently obscure, a mystery in the sense of something whose solution is waiting, somewhere in the mathematics, for someone to find it. Every generation of scientists has inherited open questions. This one is yours. The field is there, the measurement is there. The gap between them is enormous and precisely known. The next great theory of physics lives somewhere in that gap. And the night sky above you, full of galaxies and light and the distant imprint of the Big Bang, is the data that will help someone find it. Stay curious, stay awake, even when the rest of the universe slowly